Hello. In today's theory, we're looking at the development of quantum theory. So taking the idea of quanta and developing a whole theory around it. So at the end of this, we should be able to calculate the wavelength of a moving object. We're going to be looking at the uncertainty principle. We're going to be looking at quantum numbers, and we're going to be able to interpret and explain radial probability function graphs for atomic orbitals. So first, we're going to talk about Louis de Broglie. So he's a French physicist. A lot of physicists in this particular chapter. And he postulated that if radiant energy, energy in the form of waves, acts as both a particle and a wave, so must matter. If light, radiant energy, acts as both a wave and a particle, so must matter. He came up with the idea matter waves. Which will have wavelength of Planck's constant divided by mass times by velocity. Okay. So our matter waves are termed matter waves because they describe the wave characteristics of matter. Okay. And our wavelength itself is going to depend upon the mass. And this is an inverse relationship. So something large would have a very small wavelength. And on velocity. Right, so how fast it's going. Which is also inversely related to the wavelength. Okay, we're going to look at the wavelength of an electron that's moving at 0.83 times the speed of light. And mass of an electron, if we recall, is 9.11 times 10 to the negative 31 kilograms. So we're going to be using the following equation. Our wavelength is equal to Planck's constant divided by our mass times by our velocity. Now, when we're thinking about units, that h is in joules times by seconds. Our velocity is in meters over seconds. And then our mass needs to be in kilograms. The reason for this is because our joule is equal to a kilogram times by meter squared over seconds squared. Okay, so let's go ahead and check. We have 6.626 times 10 to the negative 34 joules, which are kilograms times by meters squared over seconds squared times by seconds. All divided by mass, 9.11 times 10 to the negative 31 kilograms times by our velocity, 0.998 times 10 to the 8th meters over seconds. Okay, I'm just going to take a quick detour to look at how our units cancel out. So one of these meters is going to cancel out. And then both of these seconds will cancel out with that. And this kilogram will cancel out, leaving us with just meters at the end because we put our mass in kilograms. Okay, and then when we solve for this, we get a wavelength equal to 2.92 times 10 to the negative 12 meters. Okay. Generally, we are going to look at this in picometers if we're talking about an electron. So converting this into picometers, we have 1 times 10 to the 12 picometers per 1 meter, and this gives us 2.92 picometers. Okay, let's move on to our next physicist we're going to be looking at. This is a German physicist, Werner Heisenberg. And he now is like, okay, we have the dual nature of electron. So if an electron behaves as a wave, it has to behave as a wave. So since an electron is considered a wave, and waves extend into space, and when they extend into space, we can't know its precise location. Because of this, it's impossible to determine the exact location of an electron. So this idea, we can't determine the exact location of an electron, is the Heisenberg uncertainty principle. And it's basically if we have a dual nature, that means we can't know precise location and momentum of any object in a given instant, but it's only really important for small objects. So can't know the precise location and momentum of matter, but again, only really important for very small objects, such as our subatomic particles. So let's look a little bit more at our uncertainty principle. When thinking about the uncertainty principle in terms of an atom, the uncertainty principle tells us that it is impossible to know both the exact momentum and exact location of an electron simultaneously. So once we know our velocity of a particle, for instance, an electron, we can determine the uncertainty of its location using this equation. Our delta x, that uncertainty in the location, is times by the change in our mass times by velocity, which is greater than or equal to Planck's constant divided by 4 pi. You do not need to use this equation. I'm just showing it to you. So with the mass of an electron being 9.11 times 10 to the negative 31 kilograms, and our velocity at 5 times 10 to the 4 meters per second. If we put this into our equation, then our uncertainty in the location is greater than or equal to 1 times 10 to the negative 9 meters. Now, that seems very, very small until we think about the diameter of a hydrogen atom. The diameter of a hydrogen atom is equal to 1 times 10 to the negative 10 meters. So the uncertainty in the location of an electron is greater than the diameter of a hydrogen atom. So we basically have no idea where an electron is if we know its velocity. Okay, so instead of talking about exact locations of electrons, we talk about the location of an electron in terms of probability. So let's look at what kind of like a summary of what happened so far. So first, we had the concept of quantized energy from Planck. And from that, Einstein was able to explain the photoelectric effect, and Balmer and Rydberg were able to come up with the line, and Balmer and Rydberg were able to come up with their equation for the line spectra of hydrogen. Both of these things led to the atomic model of hydrogen by Bohr, and then the atomic model of hydrogen, the matter waves by Broglie, and the uncertainty principle from Heisenberg all led to the idea of quantum mechanics by Schrodinger. He has two little dots on top. So Schrodinger took all of this and came up with the idea of quantum mechanics. So Erwin Schrodinger is a physicist, an Austrian physicist. So we have a new place, but they're all physicists if you are seeing a trend. So Schrodinger is really our father of quantum mechanics. He came up with a mathematical treatment of our subatomic particles, mostly our electron, where the wave particle duality is taken into account. And mostly really the wave characteristics. And this mathematical treatment is known as quantum mechanics. Okay? And it is the currently accepted approach for dealing with subatomic particles that behave mostly as waves. Okay, so let's look a little bit at quantum mechanics. This is also known as wave mechanics. Okay, and these mathematical equations are there to try and determine information, or are used to determine information about the energy and location of an electron within an atom. Okay, the equations themselves are known as Schrodinger's wave equations. And the symbol psi is used to describe the electron. Okay, let's look at how electrons are treated in quantum mechanics. So they are treated as waves, and we think about the electron behaving as a wave, and it's traveling around the nucleus. The electron behaves as a wave, traveling around the nucleus at some distance r from the nucleus. Okay, so our r is right here, and if that r value is correct, then when we solve for it, we get an n value that is an integer, which is what we'd expect, and we have constructive interference, which is what we want with a wave. If we are in a forbidden orbit, so our r value is incorrect, then if we put n in as an integer, we have destructive interference that occurs, which will cause the electron to spiral into the nucleus, right? But instead, it's acting as a wave. It is going around in its given orbit, and that allows for constructive interference, and it allows it to stay a specific distance away from the nucleus and doesn't spiral into the nucleus. So we finally described why the electron doesn't spiral into the nucleus. Within quantum mechanics, electrons are treated as standing waves. I'm just going to put QM for quantum mechanics, just a little abbreviation as it takes a long time to write quantum mechanics. So when we think about a standing wave, we can kind of think about it like a guitar string. And as you stretch that string, you pluck that string, it's going to have a frequency associated with it, right? And then we have within a plucked string, they have a fundamental frequency. And then they're going to have higher harmonics or overtones as well. When we introduce or we get to a higher harmonic, we get to our first overtone or second overtone, we're going to have points where we have zero magnitude. So when our wave goes through the origin, basically. And these are called nodes. So in the case of an electron, this is when we have zero electron density. Okay, so again, when we're thinking about our electron, we're thinking about them in terms of waves, and waves are going to have that synodal structure about them, and they're going to travel, but in quantum mechanics, they're not going to travel into space. They're going to stay attached at two points called a standing wave. Okay, so our wave function are going to be a set of those wave equations. And they're going to describe the properties of wave. Specifically, a standing wave, like what we have in an atom. Now, our psi doesn't give us much information, but our psi squared, so if we take our wave functions and we square it, this will give us information about the electron's location when it's in a allowed energy state. About the electron's location when in an allowed energy state. Okay, so it doesn't give the specific location, right, because of our uncertainty principle. No specifics about the location. Instead, what it gives us is a probability of finding the electron. Okay, so we would say psi squared is equal to the probability density or electron density. Okay, so let's look at our probability density. So this would be what a probability density would look like. When we solve for a probability density, it's going to give us the probability of an electron at a given point. So the probability of finding an electron, some distance from the nucleus, okay? If we have a large psi squared value, we have a high probability of finding an electron. And then a small psi squared value has a low probability of finding the electron. Okay? In a specific region. Giving our probability density as a graph is not a really good way of visualizing our probability density. So that's where the idea of orbitals comes in. Orbitals are our visual representation of probability density. So this is going to be three-dimensional in shape. And each orbital is going to have its own characteristic shape and energy. This is nothing like the orbitals that we saw in the Bohr model or in Rutherford's model, where he just talked about this distance, this circular distance, this the idea of the electron orbiting the nucleus like the planets orbit the sun. So it's not the same thing, right? Here we have this three-dimensional visual of where the electron density can be. And if you see anything that has very, very large density, it's going to have a much higher chance of finding the electron. And then as you go further and further away from the nucleus, you're going to decrease that chance of finding the electron. So you have a less likely chance of that electron being in that location, but not impossible. Okay. So our orbitals themselves, they are going to be described by three quantum numbers, which will give information about the energy, the shape, and the orientation of those orbitals. And then, as I said just a minute ago, these are visualizations of the electron cloud, not actual orbits, like in older theories. Okay, so it's not describing how an electron moves. It's describing the location of the electron. So we're going to look at the quantum numbers that describe our orbitals. So our first one is from Bohr's model. From Bohr's model, we get the principal quantum number, n. So that still applies here, which is why it's very important. We also get two others. We get L and m sub L. Okay, and all three quantum numbers can be derived from the wave equations. Okay, so they're the result of describing an orbital in terms of mathematics. So let's look at our descriptions of our quantum numbers. Of course, our principal quantum number n is going to describe the energy level. Okay. And additionally, it also gives information about the size of the orbital. Okay. So we would say that each orbital is larger than the ones before it. So we'd say that orbitals in the n equals 2 energy level are larger than orbitals in the n equals 1 energy. And they're greater in energy. Okay, so an increase in n means further from the nucleus. So the orbitals are further from the nucleus, which means the electrons are further from the nucleus, as the orbitals are our electron houses. They're what house our electrons. So if we have greater n value, we are further from the nucleus. Our orbitals are further from the nucleus. Our electrons are further from the nucleus. Energy is increased for the orbitals and the electrons. For the orbitals and electrons as well. Okay. Those that are in greater n values are not going to be held as tightly as those that are in smaller n values because they're further away and they have higher energy. Our next quantum number is L, which is our angular momentum quantum number. Qn for quantum number. Again, being lazy. And this is going to describe the shape of the orbital. So basically, what shape does the electron density adopt for a specific L value? Now, we already know that n is from 0 to infinity, right? We've already talked about that. But n is anywhere between 1 and infinity. But our L value, this is going to be based on our n value. So the allowed values for L are anywhere between 0 to n minus 1. Okay, so those are our options for L. Once we have our L values, we can talk about, and again, our L values are going to give us our shape, where L equals 0 is a spherical shape. L equals 1 is a dumbbell shape. L equals 2 is a clover shape. And then L equals 3 is kind of like a flower shape-ish. I'll show you what these all look like. But if we have L equals 0, we give this the letter S. So S is used to describe the shape. L equals 1. P is used to describe that shape of that orbital. L equals 2. D is used to describe it. And L equals 3. F is used to describe it. So if we have an L equals 0, we have an S orbital. If we have L equals 1, we have a P orbital. If we have L equals 2, we have a D orbital. And if we have L equals 3, we have an F orbital. And then last one I want to talk about right now is our M sub L, which is our magnetic quantum number. And this is going to describe the orientation in space. So if we consider Cartesian coordinates x, y, and z, it's going to describe that x, y, and z shape. So our M sub L values can be values between negative L to L. So when we think about L equals 0, we only have one possible M sub L value, which is 0, which should make sense because a sphere can really only have one orientation. Okay. When we start to go to L equals 1, our M sub L values are negative 1, 0, and 1. So we have 3 orientations. L equals 2, our M sub L values are negative 2, negative 1, 0, 1, 2. So 5 orientations. And then with our L equals 3, we have 7 possible orientations at negative 3, negative 2, negative 1, 0, 1, 2, 3. Okay. So we can take our quantum numbers and start to describe things that are called shells and subshells. So our electronic shell is our n value. Okay, so a shell describes all the orbitals at the same energy value. Right, so all of these orbitals have the same energy value. All of the ones that are n equals 1, which is only 1, but that is in the n equals 1 shell. N equals 2, the orbitals that are contained in there are in the n equals 2 shell. We have an n equals 3 shell, so on and so forth. As we increase our n value, we increase the number of orbitals within that shell. Okay, and if we have the hydrogen atom where we only have one electron, then all the orbitals within the same shell will all have the same energies. Okay, this is not true when we go to a multi-electron species, but I wanted to just describe that. Yeah, within our electronic shell, we also have subshells. And these are going to be talking about our shapes again, so our different orbital types. So it describes different orbital types or shapes in a shell. So we can have the S subshell, the P subshell, the D subshell, where each subshell describes all the orbitals with the same shape. So it describes all orbitals with the same shape. And then the last thing we have is orbitals. So individual orbitals. These are our electron houses, right? So where the electrons reside. And these are going to be these single boxes in here. So these are our orbitals. And in each orbital, you can have 2 electrons. So an orbital can house a maximum of 2 electrons. Okay. So let's look at our relationship between the different quantum numbers. If we have an n value equals 1, we only have one possible L value equal to 0. That has a subshell designation of 1s. And there is one orbital within the subshell, one orbital within the shell. N equals 2, that gives us 2 possible L values. And our subshells are 2s and 2p. Within our 2s, we have one orbital with one value. Within our 2p, we have 3 orbitals with 3 different m sub L values. So we're describing a total of 4 orbitals in our shell, but 1 within the 2s subshell and 3 within the 2p subshell. You guys should be able to come up with a full set of quantum numbers for any orbital within an atom. So make sure you are able to understand the relationship between L and m sub L. Okay. There are restrictions within our quantum numbers. For instance, when we're talking about a shell, we have an n value equal to some integer. And it'll tell you how many subshells you have. So n equals our principal quantum number, and it tells us the number of subshells. For instance, in n equals 1, we have 1 subshell. N equals 2, 2 subshells. 3 subshells, so on and so forth. And then if we have a subshell, it's going to have a specific number of orbitals. Within our subshell, the restrictions for our subshell, each subshell has a specific number of orbitals. So if we have L equals 0, we have 1 orbital. L equals 1, 3 orbitals. L equals 2, 5 orbitals. L equals 3, 7 orbitals, so on and so forth. So we keep increasing those. And the total number of orbitals in a shell is equal to n squared. So whatever n value we have, we can figure out how many orbitals are within that n value by just squaring that. So n equals 1, we have 1 orbital. N equals 2, that's 2 squared, that's 4 orbitals. N equals 3, 3 squared is 9 orbitals. N equals 4, 4 squared is 16 orbitals. Okay, so on and so forth. We can look at our periodic table to help us know at least some of our quantum numbers. Some of our quantum numbers are going to be described directly from our periodic table, and then there's some others that we can use just some simple notation to figure it out. So first, our period number will be equal to our n value. This is very important. So we start at period 1, go to period 2, 3, 4, 5, 6, 7. Right? Our period number is our principal quantum number. Next is our L value. If we have our outermost electron in our first 2 rows, we would say that outermost electron is in an s orbital or s subshell. If we are over here in the green, our outermost electron is in a p subshell. Yellow, our outermost electron is in a d subshell. And then blue, our outermost electron is in an f subshell. We can use this additionally. We can write things down in order to figure out our m sub L values. And there's one other thing called the spin, which we're going to talk about in just a minute after we go over this example. So let's try this. How many subshells are in the third shell of an atom? We want to label each subshell, and we want to know how many orbitals are in each subshell as well. So if we have n equals 3, our L values are 0, 1, and 2, so giving us 3 subshells. And then this is going to be S, P, and D based on the L value. So this is a S subshell, P subshell, and D subshell. Okay. Now, after that, we want to know our orientations. So we have M sub L. So for 0, we have only 1. For L, we have -1, 0, and 1, and 1. And then for our 2, we have -2, -1, 0, 1, 2. So each one of these are describing an orbital. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 orbitals in our n equals 3 shell. There is 1 orbital within the s subshell, 3 orbitals within the p subshell, and 5 orbitals within the d subshell. Now, all of this brings us to what are called orbital representations, so the actual visual of our orbitals. Okay, so these are our shapes of the orbitals. And remember, an orbital holds 2 electrons. Okay, so we have our, let's zoom in a little bit. We've got our spherical, which looks like a sphere. And then we have our 3 orientations, our 3 different m sub L values of our p orbital. So we have px, py, and pz. So this is our px right here. This is our py, and this is our pz. And it just describes what axis the p orbital is along. Then we have our 5 orientations for d, where we have d, x, y. then d xz, then dz squared, dyz, and then lastly dx squared minus y squared. And then we have our f orbitals, and they are very weird. They have things like fxz squared and fz cubed and stuff like that. So we're going to stop with the naming of these because they become significantly more complicated when we're talking about f orbitals. But you should be able to describe each of these here, these three, in terms of their location of their electron density lobes on a Cartesian coordinate diagram. Okay, let's look a little bit more at our orbitals. So we have our s orbital. An s orbital, our L is equal to 0. It's spherical in shape. So the radius of the sphere is going to increase with increasing n value. And now we also want to look at our nodes for our s orbital. So these are areas of 0 electron density. Within our nodes, we have two types. We have angular and spherical or radial nodes. With a s orbital, there are no angular nodes. Okay, but there are spherical or radial nodes. And the radial nodes are equal to n minus L minus 1. Okay, so if we have a 1s orbital, that will be equal to 0. A 2s orbital will be equal to 1. A 3s orbital will be equal to 2. And this radial node equation will work for any one of our different orbital types. But with our s orbital, we do not have any angular nodes. Okay, let's look at our p orbitals, which do have an angular node. In a p orbital, L is equal to 1. So we have 3 equivalent orbitals in the p subshell. So they all have the same energy. And they have a dumbbell shape. Okay. There are two types of nodes within our p orbital. So we do have angular nodes within here. So our angular nodes are going to be equal to 1 in a p orbital. And then our radial nodes will have the same equation where n minus L minus 1 will give you a number of radial nodes. And then our total nodes, since we have both angular and radial nodes, it's going to be equal to n minus 1. Okay. We also have d and f orbitals that we're going to look at very quickly. For d, our L is equal to 2. We have 5 equivalent d orbitals in the d subshell. And they have what's called a clover shape. Okay. And here, our angular node is equal to 2. Our f orbitals, L is equal to 3. There are 7 equivalent f orbitals in the f subshell. And these are some very, very weird shapes, right? So they're significantly more complicated than any of our others, our S, our P, or our D. Here, our angular nodes are equal to 3. And of course, we have our radial or spherical nodes for both of these that can be calculated by n minus L minus 1. Okay. So when we're talking about our orbital energies, if we have a 1 electron hydrogen atom, all the orbitals in the same energy level, same n value, will have the same energy. So in a hydrogen atom, which is a 1 electron species, all the orbitals within a given energy level are equivalent in energy. We call this degenerate. So they're degenerate energy. They have the same energy. Once a second electron is added in, the energies of the subshells within an energy level split in energy. While in a given shell in a hydrogen atom, such as N equals 3, 3s, 3p, and 3d, all of the subshells, all of the orbitals will have the same energy. But once you add in an additional electron, you get additional repulsions, and that causes your 3s subshell to be a different energy from your 3p subshell, which gives you a different energy from your 3d subshell. So we lose degeneracy when we add in that extra electron. So as the number of electrons in an atom increases, the degeneracy of the subshells decrease. Okay, so we have some repulsions going on, and we get something that looks more like this. We have our 1s, and then our 2s, 2p, 3s, 3p, 3d, 4s, 4p. Okay, now as we get higher in energy level, we also see that we get an overlapping of those energy levels, and they actually will get some reordering of the energy versus what we'd expect. The next topic I want to discuss is electron spin. So back in the 1920s, experiments were done, and it was found that 2 electrons in the same orbital don't have the exact same energy. They found this in high resolution spectra. So found that in a high resolution spectrum, there were 2 times the expected lines So they had slightly, very, very slightly different energies. So what happens as we take two electrons in an orbital and we introduce an external magnetic field, there is a splitting between the energies, an even more significant splitting between the energies of the two electrons, and it's based on what's called the electron spin. So because of electron spin, when electrons are introduced to a magnetic field, they either align with the magnetic field, and when they align with the magnetic field, that is a energetically favorable thing, or they repel the magnetic field, a energetically unfavorable thing, which results in this difference in energy of those significant difference in energy of these electrons when introduced to a magnetic field. So Dutch physicists George Uhlenbeck and Samuel Gouldsmith determined the electrons have an intrinsic property known as the electron spin. So this is intrinsic property determined by Dutch physicists George Uhlenbeck and Samuel Goldsmith. Okay, so they're basically spinning. They're little tiny things with their own axes, as we can see here. So what we get is what's called a spin up and a spin down. So electrons can be spin up or spin down. And because there's differences between them, there's what's called the spin quantum number to describe them. So the spin magnetic quantum number describes the spin of an electron, where spin up is a positive 1/2 and spin down is a negative 1/2. Okay, so now our orbitals are going to be described by a set of 3 quantum numbers, but our electrons are going to be described by their own unique set of 4 quantum numbers. So electrons are described by their own set of 4 unique quantum numbers. So Pauli exclusion principle states that no 2 electrons within an atom can have the same 4 quantum numbers. So if we have 2 electrons in the same orbital, they're going to have two different m sub s values. So one will be positive 1/2, the other negative 1/2. Okay, so one will be spin up in an orbital, the other one will be spin down in an orbital. And we can go back to this, and we could see our positive 1/2 and negative 1/2 are spin values for our different electrons. So any atom within here, we can describe every single electron within that atom by its own set of 4 quantum numbers. Let's try. So let's say we have the outermost electron in lithium. What are the 4 quantum numbers that describe it? Okay, so lithium is in the n equals 2 period, and it is in the it's the very first atom in there, so it is in the s block. Okay, so its L is equal to 0. Okay, s block, s, L equals 0. Our m sub L here, only one option, is 0. And then our first quantum number, it's the first atom within the s block, so it's going to be described by a positive 1/2. So we have n equals 2, L equals 0, L equals 0, and m sub s equals 1/2. We can compare this to beryllium, which is right next to it. Here we're going to have the same n, the same L, the same m sub L, but here our m sub s is going to be negative 1/2. Okay, that's everything